The following video on the sodium theory describes the nature of the action potential. Other videos in this series enable you to vary ion concentrations as you attempt to solve the puzzle that confronted Hodgkin and Huxley using the giant axon of the squid as your experimental model. Put yourself in the place of these investigators as they waited each morning for the fishing fleet to come in so that they could use fresh squid axons for their experiments. Then imagine what it must have been like in 1963 when, along with John Eccles, they received the Nobel Prize for their discoveries. Videos in this series that enable you to recreate their experiments are available on the CASEIT website. The link is in the description. To understand the sodium theory, first consider the situation where the potassium ion concentration is relatively high inside the axon, whereas the sodium and chloride ion concentrations are relatively high outside the axon cell membrane. If the membrane is now made permeable to potassium, but not sodium or chloride, what will determine how much potassium will go from the inside of the axon to the outside? Pause the video and record your answer before continuing. Since the membrane is now permeable to potassium, and since the concentration of potassium outside the membrane is relatively low, potassium will diffuse down its concentration gradient from the inside to the outside. Will this process continue until the concentration of potassium is the same inside and outside the membrane? What might prevent this from happening? Pause the video, record your answer, then continue and watch the upper right-hand corner of the screen. Although there is still more potassium inside the cell than outside, tending to push potassium out of the axon, additional potassium is prevented from leaving the axon because of the force of attraction between the positively charged potassium ions and the negatively charged fixed anions inside the axon. At this point, an equilibrium has been reached, and the force of attraction keeping potassium inside the cell has a value of negative 93 millivolts, as you can see from the oscilloscope reading above. How could this value of negative 93 millivolts be calculated mathematically? The Nernst equation can be used to calculate the membrane potential of negative 93 millivolts under these conditions. There are now fewer positively charged potassium ions inside the axon, giving the inside of the membrane an overall negative charge, since the negatively charged fixed anions cannot leave the inside of the axon. Details of the calculation are shown above. A negative value for EK means that if the membrane was permeable only to potassium, potassium would leave the axon towards the region of relatively low potassium concentration on the outside, causing the inside to have an imbalance of negative charge. By convention, membrane potentials are measured by how positive or negative the inside of the cell is relative to the outside. Now suppose that the membrane is permeable to sodium but not potassium or chloride. What factors would influence how much sodium would pass from the outside to the inside of the axon? Can you calculate what the membrane potential would be? Assuming that the external sodium concentration is 460 millimoles and the internal concentration is 50 millimoles, would the membrane potential at equilibrium be a negative or a positive value? Record your answer before continuing. If the membrane was permeable to sodium but not to potassium, the membrane potential would be 55 millivolts. There are now relatively more positively charged ions inside the axon, giving the inside of the membrane an overall positive charge. Here is how this value was calculated. In the above calculation, the equilibrium membrane potential, ENA, has a value of positive 55 millivolts. The membrane potential for an unstimulated axon is called the resting potential. An actual squid axon in seawater has a resting potential of about negative 50 millivolts, which is lower than the Nernst potential for sodium, positive 55 millivolts, but higher than the Nernst potential for potassium, negative 93 millivolts. What does this tell you about the actual permeabilities of a real squid axon? Pause the video and record your answer before continuing. Analysis of the above data suggests that in reality, the squid axon membrane is permeable to both sodium and potassium. Since the experimental value is between the theoretical limits, note that potassium and sodium have passed through leak channels. Why do you suppose that the experimental value is closer to the potassium Nernst potential than it is to the sodium Nernst potential? The actual resting potential is closer to the potassium Nernst potential because in reality, the axon membrane is much more permeable to potassium than it is to sodium. Thus, the greater permeability of the membrane to potassium means that more positive ions in the form of potassium will leave the cell than will enter the cell in the form of sodium, making the inside negative relative to the outside of the membrane, negative 50 millivolts in this example. The constant field equation can be used to estimate the resting potential, taking both the effect of potassium and sodium into account. Details of the calculation will be shown. This equation gives an estimated resting value of negative 67 millivolts for the squid axon. Assuming that the membrane is 25 times more permeable to potassium than it is to sodium, why do you suppose this calculated value is still not equal to the experimental value for a squid axon? Give as many possible reasons as you can before continuing. Before discussing possible reasons for this discrepancy between calculated and experimental results, we'll digress and look at details of the calculation. This calculation assumes that the axon membrane is 25 times more permeable to potassium than it is to sodium when the cell is at rest. The permeability ratio of sodium to potassium is 1 divided by 25, equaling 0.04. We are also assuming that the axon is at room temperature 20 degrees Celsius, at which temperature the constant defined by RT divided by ZF is approximately equal to 25, as it was for the Nernst equation examples described earlier. We'll now go back to the original question. Why is there a discrepancy between the calculated and experimental values? One possibility is that the potassium-sodium permeability of a dissected axon placed in seawater may not be 25:1 as assumed in the preceding calculation. If you substitute a 10:1 potassium-sodium permeability ratio into the constant field equation, the calculated value is equal to minus 50 millivolts, the same as the experimental result. See if you can verify this calculation. Obviously, you would need to know the actual permeability ratios to get an accurate prediction from the constant field equation. In addition, our calculation assumed that only sodium and potassium concentrations contribute to the resting potential of an actual squid membrane. And this is not the case, as you will see. We said previously that the actual resting potential of a squid axon is about minus 50 millivolts. Where did this number come from? Is this value from a single axon, or is it the average value for many axons? How important is sample size in scientific investigation? How accurate were the scientific procedures that were used to collect data? What sources of experimental error could bias the results? These are the types of questions which should be considered in your laboratory report. Since the membrane is permeable to both potassium and sodium, as sodium leaks in potassium must leak out to maintain a constant value of the resting potential. Otherwise, the inside would become more positive as sodium leaked in. In actuality, 3 sodium ions leak in for every 2 potassium ions that leak out when a membrane is at its resting potential, as you will see. If this process continued for a cell at rest, the cell would obviously run out of potassium as sodium continued to enter the axon, and the resting potential could not maintain a constant value. What does the cell do to prevent this from happening? Record your answer before continuing. Nerve cells actively pump sodium out and pump potassium in against their concentration gradients using the sodium-potassium pump. a process which requires the expenditure of metabolic energy. Since 3 sodiums entered for every 2 potassiums that left the cell, 3 sodiums must be pumped back out for every 2 potassiums that are pumped back in. Because of this imbalance, the pump makes a small contribution to the value of the resting potential, making it about 6 millivolts more negative. The sodium-potassium pump will now be activated. The axon has returned to the state it was in at its resting potential, with a relatively high potassium concentration in the inside and a relatively high sodium concentration on the outside. But what about the chloride ions depicted above? Why have we ignored them during this explanation of the axon's resting potential? Even though the axon membrane is relatively permeable to chloride, chloride is not actively pumped in most types of nerve cells. Squid axons are an exception, since chloride is actively pumped into the cell as chloride passively diffuses outwards. For simplicity, we have not depicted this process in the above animation. So far, we have explained the reason for the observed resting potential. But what causes the spike in current that is termed the action potential? The action potential is defined numerically as the total number of millivolt units between the resting potential and the top of the spike. There are 90 millivolt units between -50 and +40 in this example. For simplicity, we will ignore the sodium-potassium pump since it is not involved in the formation of an action potential, but rather functions to maintain the resting potential as we have just seen. Consider the above diagrams carefully. Based on what you already know, what do you suppose must happen to create a spike in the oscilloscope tracing above? That is, how might the inside of the membrane become suddenly very positive? Hint: remember the Nernst potential for sodium? How then might an actual membrane differ from the hypothetical membrane depicted above? At the beginning of the action potential, the membrane suddenly becomes very permeable to sodium because a brief depolarization of the membrane caused by an electrical stimulus to one end of the axon causes voltage-gated sodium channels to open. They are called voltage-gated channels because a change in the membrane potential is necessary before their gates can open, allowing sodium to pass through the channel. Let's examine this process one step at a time. The first step in the generation of an action potential is to depolarize the cell by injecting current via a brief electrical pulse into the axon. A pulse will be generated to start this process. There has been a change in the charge distribution on either side of the cell membrane as the electrical pulse has partially depolarized the membrane. If you didn't notice this change, back up the video and watch again. This causes the membrane potential to become less negative, and this change in membrane potential triggers voltage-gated sodium channels to open, as you will see. Sodium ions are now free to pass through this channel and enter the cell, causing more depolarization as they do so since they are positively charged. This in turn causes additional voltage-gated sodium channels to open, resulting in a relatively massive influx of sodium inside the axon. In reality, many voltage-gated sodium channels are open at the peak of the action potential, plus 40 millivolts in this example, driving the membrane potential close to what value discussed previously. Record your answer before continuing. Since the membrane is now overwhelmingly permeable to sodium, the membrane potential at the top of the spike will be driven close to the sodium Nernst potential of plus 55 millivolts calculated previously. The hypothetical situation where the membrane was permeable only to sodium. Since the potential will only stay at this high positive value for a brief time, what brings it back down again? In other words, how could the inside be made negative again? Record your answer before continuing. Voltage-gated potassium channels also open as a response to depolarization of the membrane, but they only do so after the opening of the sodium channels, allowing a relatively large amount of potassium to leave the axon. As the voltage-gated potassium channels open, the voltage-gated sodium channels close, preventing additional sodium from entering the axon. Look closely at the voltage-gated channels as you continue. So much positively charged potassium leaves the axon under these conditions that the membrane potential temporarily becomes hyperpolarized at a value of -64 millivolts. This is referred to as the bottom of the underswing. Back up the video to see this again, and note that the charge on the membrane has become negative again on the inside. The axon is now more negative than its normal resting potential of -50 millivolts. The voltage-gated potassium channels now close, preventing additional potassium from leaving, as you will see. Since the voltage-gated channels are now closed, what will now happen to the membrane potential and why? Record your answer before continuing, watching the video carefully as you do so. The membrane potential has returned to its normal resting potential, and the distribution of ions on each side of the membrane is back to the way it was before the generation of the action potential. This occurs because sodium and potassium diffuse across their leak channels, driven by the chemical gradient and electrical forces described previously. But how can this be? If sodium and potassium move through channels during an action potential event, haven't the original concentration gradients changed? Consider this question before continuing. The reason why the original concentration gradients have returned is that only a tiny fraction of the total sodium and potassium inside and outside the axon is involved in the generation of a single action potential, not enough to change the overall ion concentrations appreciably. As you have already seen, the sodium-potassium pump keeps the resting potential at a constant value by actively pumping potassium into and sodium out of the axon. You can now view other videos in this series to recreate the Nobel Prize winning experiments of Hodgkin and Huxley that led to formulation of the sodium theory. They are available at the CASEIT website under Action Potential Experiments. The link is in the description.